Hi, we're TEAM52. Before we start, let's have a demo to see how our model can apply to real-world applications.
運命だとか未来とかって言葉がどれだけ手を伸ばそうと届かない場所で僕ら恋をする時計の針も二人を横目に見ながら進むそんな世界を二人で一生いや何生でも生き抜いてゆこう、
Have you found some pauses and shot change text in the video? So what is shot change? A shot is defined as continuous frame taken from one camera without pause. Here are two examples, which the red arrow is defined as shot change. Shot detection plays an important role in different applications. Traditional computer vision technology may help find the shot changes. However, they cannot achieve very good results due to the complex temporal structuring nowadays videos. To solve this problem, we propose a novel supervised contrastive learning approach. Let's take a look at our dataset. All of our dataset come from official sources. Here are some of our dataset detailed descriptions. Here is how we split our dataset. The original labeling data is very unbalanced with only 1.47% of the positive label, which is very unbalanced. This is a common issue with video dataset. We first downsize the data, but this will remove too much important data. Thus, we use pseudo-label approach to generate labels to tackle this problem while keeping original information at the same time. We use pseudo-label to perform constructive learning and also solve unbalanced dataset. It not only decreases and increases the distance between frames labeled as 0 and 1, it also increases the distance between frames that are not in the original dataset and are far away from each other. We conduct an ablation study and show how each component affects the advanced score. This is our final model structure, efficient net with GRU with pseudo-label. Our input is the original pair of frame with label, along with the previous end neighbor and following end neighbor, where neighbor is our hyperparameter. In this example, we used two neighbors and input them into efficient net to extract features. Then we have GRU to extract time feature. Finally, we compare the cosine similarity and predict the shot change. Here is an example of using pseudo-label. We use efficient net because it uniformly scales width, depth, and image resolutions as shown in the figures. Our novel approach is derived from how humans inference shot changes. Humans will unconsciously memorize the plots they've seen to predict whether a specific time span is a shot change. For this example, if you only look at these two consecutive frames, you probably will believe that this is a shot change, since the scene drastically changed. However, it's not a shot change, since it's the same camera location with continuous timestamp. Without knowing the plot, it will be accidentally predicted as shot change even for humans. Therefore, we need a memorization technique. We use GRU because RNN acts like a human seeing through multiple frames and extracting time information. It will help our model to believe it's not a shot change. Before jumping into our performance, let's briefly introduce the evaluation metrics. We evaluate the models with precision, recall, and F1 score, and we focus on comparing F1 score. This slide shows the performance of our proposed model. Here we fed two original frames and 4 neighbors on the left and 4 neighbors on the right. After training on cross-entropy loss, we got F1 score of 0.88. As we expected, decreasing the neighbors from 4 to 3 would decrease the performance with less time information. We conduct an ablation study and show how each component affects the F1 score. Let's first remove our island layer, so now we don't have time information. You can see that F1 score dropped from 0.88 and 0.78. And then we remove pseudo-label and use downsized dataset. Finally, we use fixed ResNet instead of efficient net as a feature extractor. This is our conclusion. Besides generating a trailer, our model can be applied to real-world problems such as ad scheduling. Thank you for listening.